For this assignment, you're going to grade your exam that you just took in class. And so we're looking at the first problem, 1a, x times the quantity 1 plus x equals 6. You're trying to solve this. And so let's first distribute the x inside the parentheses and then set this equal to 0. So distributing the x, we have x times 1 is x plus x squared, and subtracting 6 on both sides, minus 6 equals 0. Let's rewrite this in descending order of power. We have x squared plus x minus 6 equals 0. So there's multiple ways we can solve quadratics. We can factor it if possible, which this one is. There's two numbers that multiply to give us negative 6 and add to give us positive 1. Which are positive 3 and negative 2. Since we factored it and it set equal to 0, we can set each factor equal to 0 and solve for x. So we have x plus 3 equals 0, and that is equal to 0 when x is negative 3, and we have x minus 2 equal to 0, and this occurs when x is equal to 2. So your solution should be negative 3 and positive 2. So for the next equation, we have a radical. First thing you want to do is you want to isolate the radical on one side of the equation. And so doing that, we have the square root of 2x minus 3. Let's subtract x on both sides of our equation, so we get 3 minus x. Now, since the radical is isolated, let's square both sides of the equation. If this had been a cubed root, we would cube both sides of the equation. If it was a fourth root, raise it both sides to the fourth power. But this is a square root, so we're squaring both sides. And so squaring the square root, we get back what's underneath the radical, which is 2x minus 3, is equal to, when we need to distribute out 3 minus x times 3 minus x. And if we do that and combine like terms, we get 3 times 3, which is 9, minus a 3x minus a 3x, which is minus a 6x, and a negative x times negative x gives us a plus x squared. Quadratic equation, first thing you want to do is set this equal to 0. I'm going to rewrite it in descending order of powers, and I'm going to subtract 2x and add 3 to both sides. And so we get a positive x squared, and so minus 6x minus 2x, this is minus 8x, and a 9 plus a 3 gives us plus 12 equals 0. So if possible, factor it. There are two numbers that multiply to give us positive 12 and add to give us negative 8, which is x minus 6 and x minus 2. Set each piece equal to 0. We get x minus 6 is 0 when x is 6. And we get x minus 2 is 0 when x equals 2. We are not done because we squared both sides of the equation, or if you raise both sides of the equation by an even exponent, then you may get what is called extraneous solutions. So you must go back and check into the original equation to see if this gives us a true statement or not. And so if you go back in and you check for x equals 6, we get 2 times x, which is 6, is 12. 12 minus 3 is 9. The square root of 9 gives us 3, plus x. X is 6, which is 6. So 3 plus 6, is that equal to 3? And it's not. That's not a true statement, so x can't be 6. So now let's go in and plug in x equals 2. So going back into the equation and original equation and plugging in 2 wherever we see an x, we have 2 times 2 underneath the radical, which is 4. 4 minus 3 underneath this radical is 1. Square root of 1 is 1. Plus, plugging in 2 here for x, so 1 plus 2, which is 3, is that equal to 3, which it is. So our solution is x equals 2. X cannot be 6 because when we plugged it back in, it didn't work. So going to the next piece, we have x to the negative 6th power minus 7, x to the negative 3rd power minus 8 equals 0. So looking at this, I notice that we can use substitution or a substitution to rewrite this so it looks like a quadratic equation. And so if we choose u to equal x to the negative 3rd power, recall power to power is multiplying. So this x to the negative 6th power, let's see if we can get this up here, is the same thing as x to the negative 3 quantity squared. And so we can rewrite this first term as u squared. Technical difficulties. Let's see. So we can rewrite this as u squared minus 7 times x to the negative 3rd, which is the same thing as u, minus 8 equals 0. So factor this. So two numbers that multiply to negative 8 add to negative 7 are negative 8 and positive 1. So we can factor this as u minus 8 all times u plus 1 equals 0. Solve for u in each case. So u minus 8 is equal to 0 when u is equal to 8. And u plus 1 is 0 when u is negative 1. We're going to go back up here though, and we're going to replace what u is so that we can solve for x. Recall x to the negative 3rd power is the same thing as 1 over x cubed. Rewriting that with a positive exponent. So this is equal to u equal 8, so 8. So let's multiply by both sides by x cubed to clear a fraction. We get 1 is equal to 8x cubed. Divide both sides by 8 to get the term with, get x by itself. And so we get 1/8 equals x cubed. We can get rid of the cubed by taking the cubed root of both sides. The cubed root of 1/8. Well, if you have a radical of a fraction, we can break it up as the radical of the numerator. So the cubed root of 1, what cubed is 1, all over the cubed root of 8. So what's cubed of, what can you cube that is 8, which is 2? Okay, so now let's go back in and plug in negative 1 for u. We have u is equal to x to the negative 3rd, or 1 over x cubed, is equal to negative 1. Again, we can solve rational equations by clearing the fractions by multiplying by the LCD, which is x cubed. And so we get 1 is equal to negative 1 times x cubed, or negative x cubed. Let's divide both sides by negative 1 or multiply by negative 1. We get negative 1 is equal to x cubed. And so take the cubed root of both sides of the equation, the cubed root of negative 1. So is there a number that you can cube to get negative 1? And there is. That is negative 1. Okay, so there was nothing in here that we had to do, that we raised both sides by an even power. So we're okay, and there's nothing that we could get extraneous solutions. So let's move on. Okay, so 1 part D is 2 plus the absolute value of the quantity 2x minus 5, and the absolute value is greater than or equal to 9. So we want to write our answer using interval notation and graph the solution set on the number line. So when we're solving inequalities that are has absolute values in here, we want to isolate the absolute value. So we want to subtract 2 on both sides of this absolute value. And so when we do that, we get the absolute value, of 2x minus 5 and that absolute value is greater than or equal to 9 minus 2, which is 7. So to drop the absolute value, it depends on what way your inequality is facing. And so think about it. Think about a number bigger than 7. We take the absolute value of it. Would that be true? So like 8, the absolute value of 8, is that really bigger than or equal to 7? Yes. And so to do this, we get 2x minus 5 can be greater than or equal to 7. And then it's also that 2x minus 5, let's think about this. So any number that is smaller than negative 7, and we take the absolute value, that would make it positive, and so it would make it a true statement. So 2x minus 5 is less than or equal to 7. So let's solve each inequality, and this is a OR statement. Either one of these can occur, and this would be a true statement. So get x by itself, let's add 5 to both sides. We get 2x is greater than or equal to 12. Divide by 2, it's a positive number, so we don't have to worry about flipping our inequality. We get x is greater than or equal to 6. Let's do the same thing over here. Let's isolate the x. Let's add 5 to both sides. We get 2x is less than or equal to 12. Oops, I made a mistake already. So this should have been x is less than or equal to negative 7. So if we add 5 to negative 7, this should be negative 2. So divide both sides by 2, we get x is less than or equal to negative 2 divided by 2, which is negative 1. This is an OR statement, so it could be this or this, which if we're talking about sets, we can think of it as a union. And so anything which is less than or equal to negative 1, so labeling that on the number line, would be everything shaded to the left. And then everything greater than or equal to 6. So find 6 on the number line, and it's everything greater than or equal to 6. So interval notation, we're looking at all numbers coming in from negative infinity, getting up to negative 1 and including, so bracket, union, all numbers from 6, including 6, so use a bracket, comma, infinity, parentheses. Problem 2 states, given that f of x is equal to x squared minus x minus 2, find the equation of the secant line on f of x between x equals 1 and x equals 2. So I gave you a hint there. You are finding the equation of the line that goes through the points 1 f of 1 and 2 f of 2. So we want to find our points when x equals 1 and x equals 2. And so if we look at this, we're looking at f of 1. So let's go into our equation. Wherever we see x, we're going to plug in 1. And so here we have an x squared. So I'm just going to put in parentheses now wherever I see an x, minus, I see an x here, so put parentheses minus 2. So going in and plugging in 1 wherever we see an x, we have 1 squared minus 1. So 1 squared is 1, 1 minus 1 is 0, and 0 minus 2 is negative 2. So we have a point at 1, negative 2. So let's figure out what the point is when x is equal to 2. So f of 2, so let's go in wherever we see an x. Again, let's first put a parentheses. So we see an x quantity squared, so parentheses squared, minus, we see an x parentheses minus 2. So going in and plugging in a 2, wherever we see a parentheses, we have 2 squared, which is 4. 4 minus 2 minus 2. Well, 4 minus 2 is 2, 2 minus 2 is 0, and so this is 0. So we have a point here at 2, 0. So we're trying to find the equation of the line that goes through these 2 points. To find an equation of the line, we need 2 things. We need a slope and we need a point. So we have 2 points, and so we already have the point that we need, and now we need to find the slope. And so let's find the slope of the line, and we can do that given 2 points. And so given these 2 points, we're looking at the change of y over the change of x. And so if we look at -2 minus this 0, so -2 minus 0, all over, be consistent with the point that you started with on top. You're starting with that same point on the bottom for your x values, 1 minus 2. So 1 minus 2. So we get -2 over -1, which is 2. Okay, so we have our slope here, which is equal to 2. We have a slope, and then choose one of the points. So maybe let's choose 2, 0. And so we're looking at here, when x is 2, we know y is equal to 0. So let's plug this into the equation. And so plugging this into the equation, when x is 0, and I'm plugging this into y equals mx plus b, you could use your point slope formula. I'm going to plug it in here, my y value, my slope, and my x value, and solve for b. So when y is 0, this is equal to our slope, which we just found was 2, plus b. Oops, sorry. Slope that we found was 2 times x. Sorry about that. X when y is 0 is 2 plus b. So we get that 0 is equal to 4 plus b. Subtract 4 on both sides of the equation. We get b is -4. And so looking at when our y-intercept is -4 and our slope is 2, we get back the equation of the secant line is y is equal to our slope, which was 2, times x plus b, and b was -4, so -4. So for part B, we want to find the difference quotient of f of x, which is still x squared minus x minus 2. I told you what the difference quotient was, which we're looking at f of x plus h minus f of x. That whole quantity is all divided by h. And so looking at this, when we go in and we plug in x plus h wherever we see an x, so I'm going to put in parentheses, wherever I see an x, so we have an x quantity squared minus, I see an x here, minus 2. So let's go in here and let's plug in x plus h wherever we saw an x. Minus is in the equation f of x. So the whole equation f of x, so make sure you put parentheses or brackets around that whole quantity, x squared minus x minus 2 in that bracket all over h. So if we distribute out x plus h, that quantity times the quantity x plus h, and combine like terms, you get x squared plus 2xh plus h squared. Let's distribute this negative in here. So we get minus x minus h minus 2. And then let's distribute this negative into the bracket. And so we get -1 times x squared is minus x squared. -1 times -x is plus x. And -1 times -2 is plus 2. All over h. So we're going to go up here, we're going to combine like terms in our numerator. We'll notice that all the terms that don't have an h actually end up canceling out. So notice here we have a x squared minus an x squared cancels. Here we have a -x plus an x cancels, a -2 plus 2 cancels. So all the terms we have left here is 2xh plus h squared minus h. And so notice that all of those terms have an h in common. So I'm going to pull the h out of the numerator, which would leave us for this first term just the 2x. Plus pulling an h out of an h squared is an h, minus pulling an h out of h just leaves us with 1, all over our denominator of h. And so now that we pulled out the h and this is in factored form in the numerator, this h will cancel with this h in the denominator, and we're left with 2x plus h minus 1, which is our difference quotient. For number 3, we have a piecewise function. F of x is equal to the equation x squared plus 1 if x is less than 0. It's equal to the equation 2x minus 3 if 0 is less than or equal to x, which is less than or equal to 3. And it's equal to negative 4 if x is greater than 3. So the first thing that you want to do is you want to graph this equation. And so looking at this, the first equation is x squared plus 1. Well, I know that is a parabola that is shifted up 1 unit, and I have x is greater than, or less than 0. So if I do this, I notice I have at my vertex, I have an open circle at 0, 1. And then this is going to be a parabola shape facing upwards for everything less than 0. So that is for our first equation. For our second equation, when we graph this, this is a linear line, 2x minus 3. And so if I think about this, when x is 0, I get back negative 3. So I have a point here. When x is 0, negative 3, it's included, so it's a solid circle. So let's just plug in numbers between 0 and 3. So when x is 1, we have here 2 times 1 is 1 minus 3, that's negative 1. When we plug in, let's look at the endpoint here of 3 on the other side of our inequality. 2 times 3 is 6, 6 minus 3 is 3. So when x is 3, we have a y value that is 3, and it's a closed circle. So this is a line, it's linear. And now the equation for f of x when x is greater than 3 is negative 4. And so if we have a constant, y equal constant is a horizontal line. And so when x is 3, that's negative 4 is an open circle. Whoops, negative 4 is down one more. And then we have a horizontal line as x goes to infinity. So looking at this, where's our graph of increasing and decreasing or constant? And so f of x is increasing. So we talked about this where we are going up from left to right. We are going up here when our x values, we're looking at x values when we're looking at intervals, are from 0 to positive 3. Give yourself full credit. If you use parentheses here, I'm okay with that. Decreasing, our x values are decreasing. So going down left to right, we're decreasing from negative infinity, because it's coming down forever. So we hit 0. This is an open circle, so we're not including 0 there. So negative infinity to 0. And then it's constant. Our x values where it starts to be constant is at 4. I'm sorry. It's at 3. This should be down over here at 3. Okay, so the x value where it starts to be constant, but not including getting very, very close on the left of 3, going on for until infinity. So from 3 to infinity, our graph is constant. So looking at the range of this is all the y values that you're hitting on the graph. So notice that we're hitting the y value of -4. And so let's put that in there, -4. But then there's a jump in there. So union plus. Now we're hitting all the y values in here from -3. Well, this piece hits all the that way up to y equals 3. But this goes up all the way to positive infinity. So all y values greater than 1. And so we're hitting all the y values in here from -3. Including, so we're going to put a bracket, to infinity. So part D, find the end behaviors of your graph of f of x. So what's happening to our graph as x goes off to -infinity? What's happening to your y value? So it is looking at the graph as x is going to -infinity. What's going on with your y value? Well, your y value is shooting off to positive infinity. So now let's look at the limit as x goes to positive infinity. So what's happening to the end behaviors of our graph of f of x as x goes to positive infinity? There's some value that our y value is approaching. And our y value here is always staying at -4. So the y value as x goes to positive infinity is equal to -4. So now let's look at the graph of f of x, and let's find when f of x is less than or equal to 0. And so looking at this graph, we're looking at what pieces fall below or on the x-axis. And we're trying to find what x values give us that. And so notice that it falls below the x-axis when x is 0 here, and it's included, until we hit this piece right here. So we need to know when that second equation is equal to 0. And so 2x minus 3 equals 0. Let's solve for x. Let's add 3. We get 2x equals 3. We divide by 2. We get x equals 3/2. So 3/2 are 1.5. Is saying it's including, it's less than or equal to 0. At 3/2 is equal to 0. Bracket union. And then we're hitting values that our y values are smaller than 0, starting at 4, but not including, getting really, really close on the right, to infinity. Parentheses. So problem number 4, we're going to use our knowledge about transformations and their graphs and answer the following questions. Suppose that x-intercepts of the graph of y equals f of x are at -8 and 1. So what are the x-intercepts of the graph of f of x plus 4? And so it depends on where that plus 4 is. If it's inside the parentheses, recall that this changes it horizontally, where if the plus 4 was outside of the parentheses, if it had been f of x plus 4, that would have shifted it vertically. And so the plus 4 here, it's actually opposite of what we thought. And so this is going to shift the graph to the left, which is affecting our x values, 4 units. So if our x-intercept was at -8, one of our x-intercepts, shifting that to the left 4 units, so -8 minus 4, that would be at -12. And if we look at shifting The x-intercept, that was at 1 over to the left 4 units. 1 minus 4 is equal to -3. So our new x-intercepts on f of x plus 4 in parentheses is at -12 minus 3. So part B says, suppose that the function y equals f of x is increasing on the interval -1 to 5, including those endpoints. Is the graph of y equals negative f of x increasing or decreasing on that interval -1, 5? And then give an example of a graph that is increasing from -1 to 5, so that could vary. And what, given the graph that you choose, would the graph of your example y equals negative f of x look like? Okay, so looking at this, let's look at when x starts at -1, going to a value of x equals 5. We know it's increasing everywhere on here. Oh, here's something that's increasing everywhere. So if we're looking at plugging the negative in outside negative f of x, notice that this f of x is another way to say y. Plugging in a negative in front of the y, that is changing your y values. And so if we're changing our y values, that is a reflection across the x-axis. So in our case, we'd have something here, we'd have something down here, and it would be going downwards. And so looking at this, the graph of negative f of x would be decreasing on the interval of -1, 5. So now we're going to think about it as still increasing from -1 to 5. Could be the same graph. As long as it's going up from left to right, you're good. And so now we're going to look at this and give an example where it's increasing. Is the graph increasing or decreasing? I messed up. Copying, pasting. This should have said maybe it shouldn't have. This should have said -5 to 1. I'll have to think about how we're going to change that grading. Here, if we plug in -x, we're changing our x value. So this -1 would become 1. This 5 would become -5. And it's a reflection across the y-axis. And so notice here, this should be decreasing. So the next piece, we have a point -4, 5. This is a point on the graph y equals g of x. What is the point on g of x plus 1? End of our parentheses, -3. So order matters when we're doing transformations. First horizontal shifts. This +1 says to the left 1. So we're going to subtract 1 from our x value. And this -3 is saying down 3. Going down or up is affecting our y value. And so we're going to do y -3. So we have -4, which is our x value, -1. And then we have our y value is 5, and 5 -3. So our new point is going to be -5, 2. Number 5, we have the Equation f of x equals x plus 7, all divided by the quantity x squared minus 49. Answer the following questions. What is the domain of f of x? So when we're looking at the domain, we're looking at our trouble spots. So what values can we plug in for x that would not give us back a real number? And so there's just certain areas that we have to be concerned about. And one of those are variables that are in the denominator. We can't have any variable in the denominator that sets the denominator equal to 0. That's undefined. Other things we have to worry about are radicals or logs, which we don't have in here. And so all we're concerned about is when is x squared minus 49 equal to 0? Well, let's go and let's just factor our denominator. And so f of x is x plus 7 all over, that's a difference of squares, x plus 7 all times x minus 7. And so looking at what we have in common, we have an x plus 7 in common. That's going to actually factor and cancel. But we cannot have values which set our denominator equals 0. So we cannot have values for x to be positive 7 or negative 7. So our domain are all real numbers except for x cannot be 7 or negative 7. So are there any asymptotes on f of x? Well, vertical asymptotes occur on values which set the denominator equals 0, but not also the numerator. And so notice we have factors x plus 7 that would cancel out. So only value that sets the denominator equals 0 and not also the numerator is x equals 7. And so we have a vertical asymptote at x equals 7. When we look at horizontal asymptotes, it depends on the degree of the numerator and the degree of the denominator. And so there's 3 different case scenarios. In our case, the degree of the denominator is larger than the numerator. That means our denominator is growing at a faster rate. And so if we have some number over a large number, and that number in the denominator is growing bigger and bigger faster, that's actually going to go to 0. And so our horizontal asymptote is our x-axis, or the equation for that is y equals 0. We have holes at values which set both the numerator and denominator equals 0. And in our case, that value which sets both of those equal to 0 is x equals negative 7. And so to figure out what that y value is, where our hole is, we're going to go back in and we're going to plug in negative 7 into the reduced form, even though negative 7 is not part of our domain. And so if we go in there and we plug that in the numerator we have 1 all over, I see an x there, plug in negative 7 minus 7. So negative 7 minus 7 is negative 14. So this is equal to 1 over negative 14. You could pull the negative out front, which is 1 over 14. And so we have a hole when x is negative 7. Our y value is negative 1 over 14. In number 6, we have the polynomial f of x is equal to 2x to the 4th plus 3x cubed plus 3x minus 2. So we want to answer the following questions. Find all the zeros of the polynomial of f of x. Use at least 2 different rules we used to help us to find the zeros of a polynomial during class. And then we also want to state what rules we're using. And so I tend to like the rational zero theorem, which says any rational zero, if it's a rational zero of our polynomial, then it has to be in the form of p divided by q. And so we're looking at factors of our coefficient p, which is the constant. Factors of our constant is negative 2, so plus or minus 1 and 2. all divided by q. Those are factors of the leading coefficient, which is 2. So factors of 2 are 1 and 2. And so if we look at 1 divided by 1, we get 1. We get 1 divided by 2 is a half. We have 2 divided by 1, which is 2. And 2 divided by 2 is also 1. We already have that listed, so we don't need it. And they could be positive or negative. Those will all go in evenly. So we also have another rule, Descartes' rule of signs. And so here we have 2x to the 4th plus 3x cubed. Notice there is an x squared term missing. Let's put in plus a 0x squared plus a 3x minus 2. So change the signs. Plus to plus, no plus. This could be negative. This is where it's a little confusing. It's saying that basically we could have 1 or 3. So I'm not going to use that rule. So we use the rational zero theorem. I would have to go back and look at that. I thought that 0 you could use as either way. So let's now start testing our numbers. And so if we put in a 1 here, testing our 1 using synthetic division, let's put our coefficients of our polynomial in descending order of power, placing a 0 if we have a missing term, which we said that x squared is missing. And so we have 2, 3, 3, negative 2. Bring down your first number, 2. Multiply it by our c value, which is 1. 1 times 2 is 2. 3 plus 2 is 5. 1 times 5 is 5. 3 plus 5 is 8. 1 times 8 is 8. Summing this gives us 6. Notice that all these terms are positive. So by the upper bound theorem, there's no positive number that could be bigger than 1 and can be a 0. And so we can exclude positive 2. So let's try 1/2. Oops, actually I forgot my 0. So we need to actually go back in and put in that 0. And I told you that we needed to do that and I didn't do it. So let's go back. I believe it's still an upper bound. But the 0 is going to be it's 3x cubed plus 0. X squared plus 3x minus 2. Okay, so bring down our 2. We get 1 times 2 is 2. 3 plus 2 is 5. 1 times 5 is 5. 0 plus 5 is 5. 1 times 5 is 5. 3 plus 5 is 8. 1 times 8 is 8. Negative 2 plus 8 is 6. Okay, so let's list our coefficients again. 2, 3, 0, 3, negative 2. And now let's check if 1/2 is a 0. Bring 2 down. 1/2 times 2 is 1. 3 plus 1 is 4. 1/2 times 4 is 2. 0 plus 2 is 2. 1/2 times 2 is 1. 3 plus 1 is 4. 1/2 times 4 is 2, and we get a 0 here. And so if we have a remainder, which is 0, we know that this is a 0 of our polynomial. So x equals 1/2 is a 0, and so x minus 1/2 is a factor. Notice that all of these are positive numbers, and so this, we could also say 1/2 is an upper bound. And so if I had tested 1/2 before, I would have known 1 wouldn't work. So now let's go and test negative numbers. But I'm going to test negative numbers using this bottom row of what I found x minus 1/2 was a factor. Recall that we can go 1 degree less. So we started with a fourth power. This is going to be a cubic. And so we have 2, 4, 2, 4. And what we found here, that gets us a 0, that will be a quadratic. And so let's try -1. If we try -1, bring down 2. -1 times 2 is -2. 4 minus 2 is 2. -1 times 2 is -2. This gives me 0, 0, 4. That doesn't work. So now let's try -2. So again, testing it on this bottom row, which is 2, 4, 2, 4. Bring down our 2. -2 times 2 is -4. Sum this column, we get 0. -2 times 0 is 0. Sum this column, 2 plus 0 is 2. -2 times 2 is -4, which gives us 0. And so x equals -2 is also a 0. That means that x plus 2 is a factor. This bottom row, this is a quadratic, and so this will be right here. This is going to be 2x squared plus 0x, so I don't need to put that, plus 2. This factor, let's figure out when this is 0. And so looking at this, let's pull out the 2. We are looking at when is 2 times the quantity x squared plus 1 equal to 0. Well, 2 is never equal to 0. Looking at when is x squared plus 1 equal to 0. We can use the square root method, subtract 1, take the square root of both sides. We get x equals plus or minus the square root of -1, which is I. So we found all of our zeros of this polynomial. We have our zeros are x equals -2, positive 1/2, and positive I and negative I. So now we want to rewrite f of x in terms of a product of linear and or quadratic factors, where the quadratic factors are irreducible. And so we already listed a couple of our factors. X minus 1/2 was 1, x plus 2 was 1, and then we found this 2 all times the 2x squared plus 2 was 1. Or we could factor and pull that 2 out. So let's do that. So we're given that f of x is equal to, here, this 2 all times x squared plus 1. That one was irreducible over the real numbers. We saw that it was imaginary numbers were, our complex numbers were our solutions. All times x minus 1/2, all times the quantity x plus 2. Okay, with multiplication, in this case, order doesn't matter. So if you had this in different order, it would be the same result and you would be okay. This last problem on your exam, number 7, was not a typical question I would ask on an exam, but I wanted you to give me the opportunity to show me that you learned something, or what you learned if you had studied and you hadn't seen what you had studied on this exam. This was an exam that covered 5 chapters, which was a lot of material. And so this question states, There has been a lot of material that we have covered since day 1 of this course. Take a moment to reflect on what you have learned so far in this course. Explain one concept that we have learned so far that you did not see on this test. Go into detail about everything you know about this topic. Give me a mini lesson on the topic as if you were teaching it to someone. And then give an example that could be solved when using this topic. And so this is not an example I can just go through and say this is, your solution, this is right. So it really depended on what you chose and how you went through, how you displayed your work. Was your work correct? Did you follow the directions? Depending on how many points I would give you on this. So I'm not going to go through this problem, but I just wanted to kind of go through and talk about why I gave you this problem and how you would kind of determine how many points to give yourself when you're looking at grading yourself on this problem. So I hope this was helpful. You looked and learned what you did wrong, why you did what you did wrong, if you got a problem wrong, or to reaffirm that you did something right. Hopefully this was a great learning experience, and I look forward to seeing you in the next class. Take care.